Welcome everybody to the 3D scanning and motion capture lecture. Today we're going to talk about parametric phase models. As usual, I want to start with a very brief recap about the previous lectures in order to bring a little bit of motivation why we should be working on phase models. We have been talking about deformation models. We have been talking specifically about models like as rigid as possible that provide a regularization in order to go ahead and animate and deform 3D meshes. And basically, when you want to do deformations here, you have two kind of energies, right? You have this, for instance, an RF term, the regularizer, that tells you how neighboring vertices should move along with each other. And we also have fitting terms, for instance, here provided by handles. We looked at a little bit different types of these regularizers. We looked at embedded deformations, which is a different one where instead of having these hard constraints for rotations, we have soft constraints for rotations. And then later on, we went and used these deformation priors in order to do non-rigid and non-rigid reconstruction, for instance, in the work of dynamic fusion and follow-ups, where basically the idea is, similar as in the rigid reconstruction, to have this kind of online approach where you take a depth map as input, you use the depth map in order to estimate camera poses simultaneously to the camera poses that you're estimating, also estimating the deformations, and then you're integrating these new depth measurements into your shared model at the end of the day. And that gives you a local surface reconstruction from which you, at the end of the day, can reconstruct a mesh, and you can also deform this mesh into pretty much any frame that you observe because you have these correspondences that you've optimized for. And one of the challenges that I've talked about in the previous lectures was that we have kind of a few parameters here to solve, right? It's a very difficult and challenging problem. And one reason why it's so difficult because there's so many degrees of freedom. So on one hand, we have to make sure that essentially we have freeform deformations. And on the other hand, we have to make sure that we can reconstruct the surface. So there's always this ambiguity. Did something actually move to this new place that I've just observed? Or is it just a new observation that I haven't seen before? And this makes the problem very difficult. And the difficulty, mathematically speaking, is mostly that we just have a lot of degrees of freedom that we have to jointly optimize for. And one of the things what we're going to talk about today is what I mentioned is we're going to talk about these parametric phase models. And again, quick recap from last time. I wanted to set this in a little bit of a context, why we're doing this, why we are trying to create these parametric phase models. So what we have seen right now, if you're looking at this graph here, we have seen essentially freeform reconstruction, right? We have also seen freeform tracking. So if it's starting with freeform tracking, we basically take a template that we first reconstructed, and then we non-rigidly track this fixed template over time. The freeform reconstruction is what I just described. It's this non-rigid reconstruction where we're not only tracking the template, but we're also updating the canonical space in order to integrate new observations into our model, right? And I guess you can see that this here is significantly more difficult than the tracking alone, right? And it depends a little bit on the application and which one you want to do. But I'm just trying to highlight again that here we have a lot of degrees of freedom, making it a very, very difficult problem statement. So we need a lot of regularization in order to make this work. And one type of regularization, what you can do is you can basically go ahead and have domain-specific models. And this is what we're going to talk about right now. And this is the motivation why we want to, for instance, have phase models. Of course, phase models is just one example. There's also human body models, there's hand models, and so on. But we just decided to start with phase models. And the core idea is similar to the freeform reconstruction that we want to reconstruct this model, ideally real-time, of course. But the idea is that we want to make the tracking more practical by reducing the number of free parameters that we have. And the way we want to choose these parameters is essentially in a way that we're describing the possible shapes and motion and possibly appearance of faces in a lower number of parameters. And this is done by a dimensionality reduction for the most part, right? So in other words, what we want to do is we want to find a realistic distribution. We kind of want to learn this distribution and this distribution should cover everything that makes kind of a human face a human face. So we want to only have deformations right now that can allow something that is reasonable within the distribution of human faces, right? Similar to before we had regularization priors based on ARA or ED. Now we're going to go and make this even more extreme, and instead of having these like lots of degrees of freedom, we want to reduce the number of degrees of freedom by building a parametric model, right? And the high-level idea is very straightforward. The high-level idea is, well, we just say, okay, we have a lot of vertices in a mesh, but we're going to have a dimensionality reduction, and this dimensionality reduction allows us to control this mesh by changing only a small subset of parameters, right? So it's kind of a set of basis functions, and we skin, in a sense, the rest of the mesh with respect to that. And yeah, I mean, they're simple ideas, right? I mean, I'm not sure if this is the greatest example here. You can imagine, like, if you have a rigid 6-stop post between two frames, that's a very strong prior, because that means, oh, not every vertex between two frames could move arbitrarily. We only would have 6 parameters to deform entire frames. Well, we wouldn't necessarily call it this way, but the same idea, what we want to do right now is for faces, except for 6-stop, we want to have a few more. And this is what I would like to talk about in the next few minutes, basically. Okay, so let's start. So parametric face models, in a sense, are capturing the distribution of human faces, right? That's kind of what I said, and this is what we want to capture. We want to learn a lower dimensionally or lowering approximation that figures out how to handle this distribution with a relatively small set of parameters, right? And in order to get there, what people are doing is they first go ahead and reconstruct or have a database of a bunch of different faces. In this case, what we're assuming there's no expression on the face, right? It's just a neutral face. It's just looking straight forward, and that's going to be it. So we have this face identity database, and from this database, we're having different people, meaning that every shape that we're having here has a different size, has a different shape. This is what we're seeing here. And we're also seeing we have different surface albedos or surface appearances based on the different person, right? So there's 2 types of variations that we're going to capture here right now. We want to capture different shapes of the human faces, and we want to capture different appearance in a sense of albedo of the human faces. We'll later talk about what I mean by albedo. And what we would like to do is we want to build this parametric model based on a set of these faces that we have in our face identity database. Right? Okay. And one thing we can simply do, we could go ahead and take all of these faces together that we have in our database, and we could try to compute an average face. Right? It's kind of the average face based on the samples that we're having in this database. Right? I'll later talk about how we do this in practice, how we actually compute this average face. So essentially, you have to figure out a way how to look at the vertices, at the mesh of each of them, and you also have to figure out a way how to look at the respective appearances of the surface appearance. Okay, and of course, it's a bit boring if we just have an average face, because that's not a parametric model yet. But now what we would love to do is we want to kind of encode a deviation from the average face, right? So we want to have a parameterization that tells us, oh, how does this average face essentially change? Well, and you know, that's basically what we're doing here right now. So we change that, we have like a certain standard deviation that changes the face shape in a certain way, right? For instance, if I go down here, right, it looks a little bit smaller. If I go up here, it looks a little bit larger. So you see how the shape between those ones has changed, right? Again, average face, and then you go into these 2 directions, right? And coincidentally, these directions here also change kind of the gender a little bit. You see, this is more like a female face, and this is more a male face, whereas this is more kind of like quote-unquote gender neutral. It's not necessarily that these models are constructed with that semantics in mind, but they could be in principle. And based on the human distribution of the faces, this is inherently also a little bit given the way how these models are being constructed. Okay, so this is essentially the shape, right? And this one, as you see, the surface appearance here is always the same. So this axis here is only changing the geometry. It's only changing the identity. Whenever I'm going to talk about the identity, that means same expression, same appearance, different geometries underneath, right? So it's changing the identity, which person is it, but I'm not changing the appearance in this case, right? But of course, we also want to change the appearance. So the second property of such a phase model, what we want to have is we want to change the appearance. And that's what we're going to do here. Okay, so the shape defines who you are. And in this case, we also have the albedo encoded, which means in this case, the skin tone, for instance, gets a little darker, and in the other direction, the skin tone gets a little bit lighter. Now, you have to imagine that, of course, we drew these two axes here, that one of them is for the shape and one of them is for the albedo. But of course, just the albedo alone, sorry, just the shape alone, has, of course, a higher dimensionality. This is just not one scalar that controls this where you are here. You have to imagine that this is a higher dimensional vector that allows to control the shape in a multidimensional fashion. And same for the albedo here. I still want to quickly iterate for those who don't know what an albedo is. So in this case, we are modeling the reflectance of the human skin, basically, of the face, right? And since modeling human skin is actually really difficult, so in principle, you have very complicated rendering models and graphics, right? So you have like some subsurface gathering, you have very complicated ways how to render it. We don't do this for these phase models at this point. So these phase models are modeled with a single albedo, and albedo means this is essentially a diffuse reflectance function that tells you the appearance of the face, right? So this is basically just an RGB value that is dot producted with the light vector in the normal, and this is just the diffuse lighting that is being used for the most part. There's more complicated versions or more powerful versions of this, but this is what the basic parametric phase models use, because that makes the parameterization a lot easier, allowing for easier optimization later, and we'll talk about this in a little bit more detail. But yeah, so if you don't know how the rendering stuff works, it might be useful at this point to quickly look up some graphics content here, like how to generate shading with a diffuse shading model. And this is something what the albedo here is being used for. Okay, but the bottom line is what I wanted to get at. We essentially have these two axes here. One is for the shape and one is for the albedo, and this is defining your shape identity. And each of them is a higher dimensional vector that allows you to control those two, right? And now I would love to have kind of a third axis here, but since I'm not good at drawing, we just have to imagine it. We're going to add a third axis here, which is essentially now looking at the expressions, right? So this is based on what we've done before is we had different people all looking in the same neutral pose. Now what we're going to do is we're going to take a single person, and this single person we're going to record in different expressions. And this is what our face expression database is going to give us, right? So now we have these different faces here. Well, it's always the same person, but we have different expressions of that very same person, right? And essentially, again, what we want to do right now is we want to add a third axis here that adds an expression vector that not only allows to control shape in albedo, but also allows to control the expressions at the end of the day. So you have to imagine we have another vector here, or another axis, that goes and controls the facial expressions. Very similar than before, right? In this database, we just, however, have only one person, but from this one person, we have different expressions. Okay, so I'm going to later explain how these things are being constructed, but I wanted to first show you some examples what it means if we had already reconstructed such a phase model. I wanted to show you what you can do with it based on a given parameterization. Okay, so here's a very simple example, right? So this is a parametric phase model. And what you're going to see right now is you're going to see that this phase model here is being animated. And by the animation is what you see here on the right-hand side, you see a bunch of sliders. And these sliders here, they're going to control a bunch of parameters. These are the parameters from our model. And if you're looking closely, this one is the shape, this one is albedo, this one is expression, and this one is illumination. So let's ignore illumination right now. We haven't talked about this one. I'll talk about this later, but let's do it step by step. So we've talked about the shape, we've talked about the albedo, right? Again, if I'm going quickly back here, this is these two axes here, it's shape and albedo. And we talked about expressions, which we also wanted to add. And now These are a bunch of sliders that respectively control the vectors for shape, albedo, and expressions. And what we can do is we can basically put all of these parameters, we can put them and stack them in a single vector P. And this is the parameters of our parametric model. Now, I didn't tell you all of them yet. The simplest parameter actually that we're going to use here is not part of any of these. The simplest parameter is just simply the rigid pose. And that's what you have been seeing in this animation. It's not super complicated. It's just a 6th of rotation and a translation. And the idea here is that based on this rigid pose, you can rotate the parametric model accordingly, just a rigid transformation. And here at the bottom, what I'm going to write is, I'm going to always write how many parameters are being used for this specific model. Now, if we're having a rigid transformation here, like a rigid pose, we know we have 3 parameters for the rotation, and we have 3 for the translation, respectively. For the other parts right now, I'm going to now add more and more of these parameters by simply modifying these sliders. However, be careful that I'm going to tell you how many dimensions are being used here, but this is just one specific example that was used here that doesn't count for every facial parametric model. It's just one example to give you a little bit of an idea what the dimensionalities of these vectors are. Okay, so let's start with it. So we have a rigid pose. Again, that's what you can see here. Now what I want to do is I want to change the shape identity. That's what you can see here. So we have here the alpha parameters. You see that here the shape is being modified, right? And you see that the shape of the model is changed accordingly with these sliders. So the first slider is basically scaling it up and down. That's a very easy one. And the other ones are having a little bit of different effects on the shape, right? These are having more subtle effects, but changing as a combination here, changing effectively the shape of the face, right? And what I mentioned is in this specific case, there's a bunch of sliders here, but in total for this specific model here, they have been used an 80-dimensional vector that represents the shape for this specific model here. Okay, right. So in principle, very straightforward, right? We have a bunch of parameters to control the shape. We modify these sliders, and these sliders basically control these parameters. And based on that, you see how the geometry of this mesh is changing accordingly. Okay. Now we can do the same thing with the albedo actually. So these are these sliders here. We're going to look at those ones right now. So now if you're changing the albedo, you're seeing a similar effect in a sense. Different albedo sliders here have different effects on the respective parts of this parametric model, right? And similar as before, you're seeing the top slider in a sense has the most effect. That's basically making it darker and brighter. And the other ones are having more subtle effects to get more fine-grained control, how to change the respective albedo properties of this face. And similar as before, this beta vector here has also an 80-dimensional vector. So in this case, we have 6 parameters for the rigid pose, we have 80 parameters for the shape, and we have 80 for the albedo. And again, these bunch of sliders here, they just control the respective first 5 of these 80 parameters, right? So the lower parameters we would have here are not even modeled by these sliders, but they would also have a certain effect. But the first sliders, they have a larger effect. That's just the way how these models are going to be constructed. And we'll talk about this in detail. Okay, now I wanted to go to the expressions. Okay, here we have an expression vector. So in the expression vector, same game as before. We're keeping everything else fixed here. And now we're going to change the expressions. And you see that different sliders, again, have different effects on the respective expressions of this person, while not controlling any of the albedo and not changing the shape at all. So the core idea is here that this identity of the person stays exactly the same. It's the same person, right? It doesn't change like to a different person, but we can control the expressions of that single person here, right? In this case, this is about 76 parameters. Again, this is just one example here. And these parameters are being controlled with these sliders again, right? So you see, okay, now we have a bunch of animation parameters where we can use in order to control the expressions of that person. Okay, so what do we do next? well, we have most of it done. There's one thing I haven't talked about it at all, but these models typically have those. So we have to introduce that too. So in order to get a realistic appearance of these models, you also want to be able to shade them. And for the shading, you need to do lighting. And this is a thing that you can do with another few sliders. So you can change the surrounding lighting here in order to control lighting, to generate lighting effects, in order to make the face appear in certain different environments and to simulate the lighting of the respective environment where this face was in. And now I can already see, now it looks a little bit more like a real face. Again, it looks a little plasticky, right? But we're getting there, right? So you see, we are getting there. It's one by one how we're approaching this. In this case, these lighting parameters are 27 dimensional, right? So if you're adding it up, we have a few hundred parameters here in total that control the parametric face model and allow us to basically go from these parameters P to render this image out of it and control the shape, the albedo, the expressions, and finally the illumination. Now, I wanted to go basically now one by one and explain these parameters, what they actually do in detail. And I mean, the rigid pose I don't have to explain at this point. I think everybody knows, okay, it's a rotation translation, that's straightforward. But I wanted to start explaining how the illumination parameters look like, because that's something we haven't really talked about yet in this lecture, but it's actually a quite important concept in both computer vision and computer graphics. Okay, and in order to understand how we model the illumination here with these 27 parameters, you have to understand what illumination models basically are doing, right? So the idea here is that you have kind of a 3D face. You have at some point, you have some sort of light source being defined or some lighting condition being defined in the environment. And you have some camera that observes the face here, this virtual 3D model. And the idea is that based on this observation and based on the lighting, you apply some shading. So you consider the lighting here, and then you can actually go ahead and shade the whole thing, and then it looks something like this, right? And then you can render out an image that ideally reflects, for instance, what the observations were. Now, we need to talk a little bit about illumination models. I won't have time to go into too much depth here. If you're interested generally in illumination models, again, I would recommend look into computer graphics lectures. They're gonna have some more information how BRDFs are being used, how shading is being done, and what kind of specific lighting models are being used. But I wanted to talk about one specific lighting model a little bit in more detail that is critical. So the first thing what we have to understand, lighting in faces is complicated. It's very, 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 very complicated, right? And I mentioned this already. You're going to have things like subsurface scattering. You're going to have specular highlights. Like, for instance, you see here, like, on my head, you see my hair. You see that I have a strong light on the top here of my head. So you see a lot of weird reflections. You see reflections here in my eyes even, and so on, right? So you're going to see that lighting in a face is really complicated. It's not so straightforward to do. And actually, in fact, there have been researchers looking at proper rendering of synthetic faces for the last 5 decades, and there's been a lot of work in order to get this to look realistic. That's basically the stuff you see in Hollywood movies today. Yeah, so you need advanced light transport models in order to make sure this works. However, what we can do here in the context of these parametric face models, we can look at simplifications and approximations of these complicated lighting models. And there's 2 very simple ones I want to talk about. One of them are environment maps, and the other one are spherical harmonics. These are the 2 ones I think that are relatively important. Okay, and what they do basically is they leave a lot about the complicated math here out that you have in like light transport methods, and you would need heavy ray tracing for in order to render it, but we want to simplify it a little bit. So the first idea is environment maps. That's straightforward. That's being actually often used in the context of faces, because what that means is, assuming you kind of capture a panorama image of of your environment, and you're treating this kind of panel image as the incident scene lighting, right? So if I take an image, in a sense, everything that comes to my camera is kind of considered to be lighting. And in this case, this panorama image is an environment map that represents the incident lighting at a certain point that is being received from the surrounding scene. So that's the scene lighting. And what you can do is you can take this incident lighting and parameterize it accordingly. And there's different ways. There's things like cube maps, sphere maps, and these are concepts that are typically being used in computer graphics in order to parameterize the access to the environment maps in order to map them to the respective meshes for the final rendering. And you can do this with, again, cube maps, sphere maps are very common. There's other ideas, but these are the most common ones. And the assumption here is essentially, well, our lighting is kind of distant. It's infinitely far away. There's no self-shadowing. There's no scattering whatsoever, right? It's just basically, I'm assuming the scene is infinitely far away, and I have zero interaction with the scene here, right? So if you're taking this example, there's like this tree here, right? And this tree, I can't interact with it. I can't go behind it. I can't have like self-shadowing with the tree here. I'm just assuming everything is infinitely far away. So this is relatively straightforward and can be done on actual real images, right? You can take a pano image and you can map this to an environment map. But the core idea is always the same. The core idea is you have kind of the observer, or the receiver in a sense, is in the center, and everything else is infinitely far away. At least that's what the model says. And then you have this incident light. And now what you can do is you can actually go ahead and take these photos. That's one option. But when you want to parameterize arbitrarily these environment maps, you can kind of find a basis function that you can parameterize, again with a low-rank approximation, that kind of approximates the idea of having a single observer and receiver in the middle, and you have a lot of incident light coming in. And this is the idea what spherical harmonics are doing, right? So the idea of spherical harmonics, it's basically an orthogonal basis, and it's also defined over a sphere. In a sense, you could imagine it's kind of like a parameterization of environment maps, right? But it's a very low-rank approximation, right? So you will not see like any detail and sharp changes in lighting. It's a very smooth approximation. And the idea is that you simply parameterize the lighting over the sphere, right? You just simply find a reasonable parameterization over a sphere, and you're selecting a bunch of basis functions over the sphere that you can linearly combine. And this is what spherical harmonics are doing, right? So you have these spherical harmonics basis functions here. It's typically this pyramid, right? At the beginning you have one, at the next they're called bands. You have one here, you have three here, and so on, and this continues, right? This pyramid would grow wider. And then what you do is you have a linear combinations based on these basis functions with a series of coefficients. So these pi here are the basis functions you're combining, and here are the coefficients that are multiplied to the basis functions, right? So this is the combination here based on the current coefficients. You're going to go from here to here. And what these spherical harmonics are doing now, they're essentially parameterizing the sphere based on this linear combination of these basis functions. And I already mentioned they're assuming kind of a smooth version of lighting. You can make it higher frequency if you're adding more of these bands, but if you only had the first band here, it's just dark and light. That's it. And then here you're having more variations. And the assumption here is that the surfaces are going to be Lambertian. So the question is, how can we use the sphere parameterization of these spherical harmonic spaces in order to model Lambertian lighting? Well, Lambertian lighting means that the lighting is not dependent on the respective viewpoint, but it's only depending based on the surface normal and the incident lighting. And the incident lighting is modeled by the spherical harmonics, and the normal here is given by the respective mesh or the respective geometry, right? So, okay, so this is Lambertian lighting. We're going to have a normal here, we're going to have a surface here, and what this means, Lambertian lighting, is you have here some incident light, and the light is reflected in a uniform way, right? So no matter where I'm going to look at it, this surface point will always have the same brightness. In the opposite of Lambertian lighting would be a specular reflection, right? If I have a specular surface, then I see a few dependent effects. And in reality, a lot of surfaces are going to be diffuse, they're Lambertian. Diffuse and Lambertian surfaces is equivalent, right? And yeah, so we're going to assume, however, in the spherical harmonic spaces that these are going to be diffuse. Okay, and we're also going to assume for the spherical harmonics that we have this distant smooth lighting. It's kind of like the environment maps before, so we're assuming everything is kind of infinitesimally far away, and we're going to have smooth lighting. And the lighting is now simply a computation based on these bases here in combination with the normals, right? So the lighting is computed by taking the spherical harmonics coefficients. These are part of our parametric models based on our basis functions. The basis functions are a function based on the surface normal, nothing else. There's nothing else in it. It's just the surface normal alone determines what the lighting is going to do given a set of coefficients. Okay, and now what we're going to do is, in order to model the lighting, we're going to change these coefficients here with the sliders, right? These coefficients we're going to change. This, again, the normal is fixed, right? I mean, in this case, they don't change. And the basis functions are also fixed functions. Okay, and this is what we're going to do here, or what we have done here already. Right. So now this is the first band of the spherical harmonics at the top, and these three sliders are the next band, and so on, and then it goes down and down, and we can change the lighting accordingly, and based on that, we're going to get different appearances. Again, I wanted to really highlight that this is not a photorealistic way to do lighting, but it's a very simple approximation, which we will later see is quite useful for these phase parametric models, because they're very low dimensional, and we can fit them very easily to the respective targets. Oh, and by the way, here you see a visualization of the spherical harmonics, right? These are the spherical harmonics coefficients that we have changed here. So I can go back here and show this again, right? So yeah. Right, so you see here how this one changes, and so on. Okay, so we've talked about the lighting a little bit. Actually, if you're interested in these kind of 3D reconstruction areas, spherical harmonics is a pretty it's a pretty widely common lighting model that is being used generally for reconstruction, because it has this regularization property, as assuming smooth lighting, that we can use essentially in order to get good reconstructions later on when we just have sparse observations. Okay, now I wanted to talk a bit about the rest here. I wanted to talk about the shape, the albedo, and the expressions. And specifically, I wanted to talk about this super famous work, which is this Blanz and Fetter work. It was published in '99, right? So it's about a little over 20 years now ago, right? And this Blanz and Fetter model is extremely popular. This was one of the first that kind of encouraged this idea of having these parametric phase models. So this, I think, is a very pioneering work. And the idea here is that what you do is you basically have neutral 3D scans with a very high quality scanner of human faces. In this case, you're taking 100 male, 100 female candidates that you want to scan. They all assume to have the same expression. So if you're going back here quickly, that's only shape and albedo we're considering. We're not yet considering the expressions here, right? So this model is only doing neutral ones here right now. And then what's happening is we have two independent Pca models for the identity, right, for the shape, and for the albedo accordingly. Now, I hope it makes a little bit already more sense, because now I'm mentioning suddenly that these are Pca bases, right? And Pca bases have this property that you basically do a lowering approximation of a distribution, and then you're getting eigenvectors. And these eigenvectors, they span a basis, and you can control that basis by controlling the coefficients to it, which are the eigenvalues of the covariance matrix here. And the idea here is these sliders are these coefficients that are attached to the eigenvectors from this Pca model, and we can control it. And since this is a Pca basis, again, we'll talk about this again, how this works a little later, But the idea here is that the first one has the most variation, so that one will make the biggest changes. And then every other slider will have a smaller and smaller effect on the final output. In this context, I wanted to say, like, this is really, really cool work, but I think we have to be also very careful right now because we're talking about human faces. This is not a general distribution of all human faces. So there's actually a massive bias in these 200 scans. So basically gonna have mainly Caucasians in there. Very few, actually, I don't think there's any Asians in it, to be honest. So it's a little bit of a problem using the data in a sense to have, like, you cannot expect to generalize to all humans, right? I just wanted to make this very clear. And whenever we're dealing with data like this, we have to be very, very much aware of it. But as a research, this was one of the first works, and this is why it had a lot of impact and is still actually often used. If you're going further, we also have another drawback that we should talk about, since this is a Pca basis, the parameters have global influence. In other words, if I want to just change a wrinkle here, it's not going to be that easy. I will have to change a lot of parameters in this Pca basis to get this desired effect, because a single parameter in the Pca basis is always going to affect the whole face, right? So parameters always have global influence because it's a derivation of a Pca basis. Okay. There's also no real semantic deformations, right? There's no semantic meaning to it. We'll later see a little bit. There's some abstractions, like, you know, for the shape, the first eigenvector is basically a scale. That's just the largest variance in human faces that is being used. Okay, so I've talked about this morphable model of Bluntz and Fetter, and since then there have been many, many works that have expanded on it. And one very popular work that has to be mentioned here is blend shapes. And blend shape is a thing that has been, I think it's probably still the state of the art right now, that most people are using for face modeling and face reconstruction. And this is a core difference what we have just seen to the Bluntz and Fetter morphable model, in the idea that this is an additive model. What does it mean that you have an additive model? Well, assuming you have a bunch of expressions, you can of course go ahead and well, first of all, it adds the expressions, right? That's the first thing. And this additive model, instead of modeling a Pca basis over all of these independent ones, the idea is you're starting out on a neutral face first. That's given by your shape, right? So it's basically given by the Bluntz and Fetter morphable model, or whatever people have been using. And then the idea is that from this neutral phase, you are adding respectively in order to get the expression. So you're having basically offset vectors, and these ones are controlled via blend shape weights, right? And these blend shape weights is just a sum that can be computed as a linear combination between different scans of one person, right? Could also do it with multiple people, actually, but there's different variations of it. So basically, with the neutral phase, you have a linear combination between those ones, and this is what you're getting out of it, because this is like input plus linear combination between those gives you that one, right? Okay, and these can be nicely customized. There's actually a lot of work how to control them, how they give you good results, how to regularize them, and so on. And one popular choice here is these delta blend shapes, basically, where this is, you know, you're just basically having these offsets from the neutral phase here, right? And what the high level thing here is, what's really important is, we have two parts right now. We have this morphable model that is defining the shape and the albedo. We have the blend shapes that define the expressions. And we also talked about how lighting works, right? So if we are going to this whole thing together right now, we have all of the parameters together that I've explained. So I wanted to, you know, like, I mean, I can't go into all papers there in detail right now, but I wanted to give you a quick overview. There's actually a lot of different work in these parametric models, right? Human faces are really important for many applications. Reconstructing them accurately is super important in the movie industry. It's super important even on phone applications right now, when you do things like relighting of photos right now, visual makeups, 3D reconstruction of people, and stuff like this. The human parametric models of faces is a big deal. And this is why I wanted to very briefly give you a bit of an overview of the digital landscape that has been done there. So basically, we have two kind of axes here. We have like, the generalizability or generality axis, and we have more the semantic axis, right? And there's been a bunch of different models, right? So if you're thinking about the morphomal model, pretty general, not that intuitive, has no semantics, basically. There's multilinear models like by Vlasic, Kao et al., Shi et al. We also have these blend shapes. They're becoming kind of more semantically meaningful, right? It's like Chorito, Wu, Tees. And we have phase rigs that are going more into higher quality captures in order to have more semantically meaningful control of these models. And there's like these adaptive blend shapes. There's a bunch of work out there. I'm not going to go into all of the details, but I wanted to give you a little bit of an overview of the landscape, that there's a lot of things going on. And if you're looking at these publications, they're ending around 2016, 2017. And this area is not done yet. But the reason why I didn't want to add more here is more of the recent work would use a lot of deep learning. These ones are not using any deep learning, basically. This is just classic Pca. By the way, Pca is also a learning-based model, right? A lowering approximation is modeling a distribution of your training set in a sense. This is also, there's been a lot of work right now with deep learning, but in all fairness, a lot of the phase reconstruction is still being done with these classical models. So we have to be, I don't want to make it into a new deep learning lecture. I will later on talk about a bit the connections there to deep learning and what the relationships are. But at the moment, the deep learning-based model more or less trying to approximate those ones. This is also something that we're doing in our own research, because we are working basically on neural parametric models, right? And I think this is a very exciting research area. If you're interested in that, of course, ask us. We always have cool research topics in this area. But I didn't want to go into too much detail there. I just wanted to give you an overview here of the classic methods. Okay, what do we have right now? Well, we have our amazing parametric phase model. And this parametric phase model has a bunch of parameters. We have here our phase model itself, we have the illumination, and we have our image formation model, right? So these two things from an image formation model is clear, right? This is our rigid pose, RNT. These are our intrinsic parameters defining the camera. We talked about the illumination model, the spherical harmonics coefficients, and we talked about all these parts of our phase model, which has identity, geometry, albedo, and expressions, right? Well, identity is part of the identity is geometry, and part of the identity is albedo. This is our identity that we care about in order to make a person this specific person, and then the expressions is going to be the respective animation underneath. All right, that's what we want. And now we're going to talk about how they're being reconstructed in practice, because that's something we haven't done yet. So now we know what they should do. We know how they're being parameterized, and we know the effect of the parameterization, what it has on top of the model, right? Okay, and typically what we have in these parametric models, we have two parts. The first part is this offline phase where we can construct them. This is what we're going to talk about right now. And the second part, what we have is, once we've constructed them, we can use them at runtime in order to fit the models to some targets. In a sense, it's a little bit like machine learning, right? This is a learning phase. We're learning our model. And then we have a test phase, a test time. We're going to go ahead and fit the model to some target image, some target RGBD map, and stuff like this. Okay, I want to talk about this first part right now. In fact, the second part we're going to talk later. I'm actually going to talk about it in the next lecture. But I wanted to talk about the model construction first, because it's surprisingly using a lot of tools that you have already learned in the previous lectures of this course here. Right, so how do we do it? Well, a few things are spoiled already. So we want to build basically a Pca model. But how do we do this? A Pca model of what, right? So let's just make a few assumptions. I want to simplify this a little bit when we talk about it. So assuming we have a bunch of meshes of the face, they exactly have the same topology, the same connectivity of the geometry, right? The same number of vertices, same number of faces, and you're going to have one-to-one correspondences between the vertices, but the vertices between those different poses have, because they're different poses, they have different positions, right? So we have multiple face models in different poses, but they have one-to-one correspondences between the faces, right? And what we can do right now is we can say, well, we can compute basis functions of a PCA-based model, and that gives us essentially our phase parametric model. That's what I said, right? So we're taking these one-to-one correspondences, we're computing a PCA over the vertices, and that's our model. Now, unfortunately, it's not that straightforward, because in practice, we have to find a way first to get these meshes here. This is actually the hard part. This is not so straightforward. Like, how on earth do we get a set of meshes with the same topology with one-to-one correspondences in different poses? So that's one part, right? And then once we have that, we can go ahead and compute this phase prior. And well, computing it in practice means, I'm going to go into more detail right now, is we're going to scan a couple of hundred people with 3D scanners. Again, very similar to what we have seen in the previous lectures. And then what we do is we actually go ahead and fit a topologically consistent template to each of the scans. Okay, what does it mean? Well, assuming you're going to have 100 people, you did a 3D laser scan of them, and of this laser scan, you're going to get 300, going to get 200 or whatever scans, one for each person. And now what we like to do is we like to take a single template mesh that we non-rigidly register with each of these scans. And what we get as the result there is, from this template mesh, we're going to get the same template mesh in different poses. And that's exactly what I said before, right? If we're going back again, this is our assumption. Now we have, after we did this non-rigid registration to these scans, our template mesh that has always the same connectivity in every frame has one-to-one correspondences between the vertices, from which we can compute a PCA basis for identity and expressions. Yeah, and then once we have that, at test time, we can fit it to input data. Okay, little bit more details here. For the test time, again, we're going to talk about this a little bit later. You can do this once you have it. Once you have this regularization, you can fit this to sparse set of key points. You can do this from depth data. You can do this from RGB data. It depends a little bit on your setting. Again, not going to go into too much detail right now. I decided to split this up and move this to the next lecture. Okay, but let's talk about this first part. I want to talk about this part a little bit more detail. I want to see where we are on this end. Okay, so how does it work? This is a cool laser scanner here, by the way. Super cool. Looks really fancy. Okay, so the way how this works is we want to compute this phase prior by scanning a lot of different people. That's what I mentioned, right? And I said, okay, let's say we scan 100 people. And now what we want to do is we want to hire an artist. And this artist is going to model us a really high quality face template. And this high quality face template, we're now going to non-rigidly register against each of these scans independently. You might ask, well, how do we do this? Well, it's actually straightforward. We are doing it with the methods we've seen before. We have these non-rigid template alignments, we have the RGB registration, we have the ED alignment, and stuff like this. I'm not saying there's one of them that all of these methods use, but I'm saying you have to find a way to non-rigidly align this template with all of these scans independently. Right? So in practice, that's what we're getting here from the scans. It's just an example, right? This was this fancy scanner here. This is this cyberware laser scanner. These are scans you're typically getting here, just to give you a bit of an intuition how this looks like. And actually pretty funny if you're interested. At some point you can stop by in our lab. We've bought a bunch of these laser scanners now too. And we're scanning people, and it's kind of fun. So yeah, I mean, I think this is super exciting. And based on these laser scanners, we're getting the geometry here from each scans, and we're also getting a rough color approximation here. And what we can do is we can then again use those ones as a target to align this artist model template mesh, right? And it's actually kind of interesting. You don't actually have to do this with a laser scanner. You can actually do this with commodity sensors too. And this is also something we have seen already. So what you could do is you could take a Kinect Fusion scan of a static person and just get a static reconstruction of this one person in this one pose. This is what this is doing here, right? These are the respective Kinect fusion scans of one face in one pose. And then what you could do is you can align the template mesh against those ones respectively. This work is called Phase Warehouse. This is particularly interesting because this actually has a little bit more diversity than the other ones. There's a lot of Asians in there, and this is a quite broader basis than what the other ones had, and they have more scans because they're super easy to do with the Kinect fusion scan. Now, I also want to show quickly how this looks like, this template mesh. So this is the template mesh, by the way, right? And this template mesh, as you can see, is now non-rigidly aligned to these underlying Kinect fusion scans, right? This is what's happening here. Okay, right? This is just input RGB to just show you how these people look like. These are the Kinect fusion scans done with the Kinect. Again, person sitting statically, not moving, move the Kinect around a couple of times. This is the scan you're getting. And this one here at the bottom is a template mesh that is non-rigidly registered against these respective Kinect fusion scans. And between those ones here, we're going to have one-to-one correspondences. Here's an interesting example. This is the deformation error, by the way. So this is the template mesh trying to get aligned here. This looks pretty good. If this one is aligned here, you see the hair here doesn't quite fit, so we have a high error here. Right? This is this non-rigid registration. Right? Okay. So this is our template mesh being non-rigidly registered successfully by using all the techniques from the previous lectures. And as a result, what we're getting right now is for each scan here that we've done, we're getting this alignment of the templates. And what we're doing now is we're just taking all the vertices of this template mesh. Let's call this V0, right? This is just a vector. This is vertex 0, then vertex 1, vertex 2, and so on. In this specific pose here, we're just writing this one into a single vector, right? These are all the vertices of this template mesh. These are all the vertices of this template mesh. And this template mesh is the same topology, of course. So the dimensionality of these two vectors is going to be the same, right? And these are the vertices of the respective deformed template mesh. These are the vertices of the deformed template mesh here, right? And now we're getting a little bit closer. Again, remember what we've done. We've taken Kinect fusion scans here first. We have aligned the template mesh non-rigidly. We took the vertices here and put them in a vector. Did the same for the other frame, and we did this for every frame. And now what we're doing is we're computing a Pca of that. Finally, our great moment has come. And we're doing this for the identity first, and we can do this for the expressions later on, right? But let's talk about the identity first. That makes things maybe a little bit easier to conceptualize it. Okay, what does the Pca mean? Well, we're getting an average vector. Now the average phase, remember at the beginning of the lecture, I talked about the average phase that you want to compute on a bunch of phases. Now it's pretty straightforward. Now we just have these m vectors here of vertices. We can just average them. This is straightforward, right? So we just compute the average by summing them all up and dividing it by the number, dividing it by n here, depending on how many poses we have. We can compute the principal components and we compute the standard deviation. Okay, how does that work? I guess I can explain the Pca very briefly. First thing what we do is we compute the mean. Imagine all of these points are high dimensional points that store these like vertex vectors that I've just said. First thing is we're computing the mean. We just sum them all up, dividing by n. And then what we're doing is we are mean normalizing each of these points. So we're taking each of these xi points and we're subtracting the mean from it. It's the mean normalization. This is the first step, what you do in a Pca, right? So we're having this mean here, and that's what we do first. And then what we do is we do compute the principal components of the dataset. Next step, what does a principal component mean? Well, we're basically trying to find the vector here where we have the highest variance along the vector, right? So along this vector here, this direction here, has the highest variance across these points. In the context of our phase meshes, that means there's the most variation in the poses here. And in practice, what you could just compute that, right? That's just it's just the least squares optimization. So we're searching the direction that minimizes the distance of the projection of these points here, right? So basically, we want to minimize those ones here, right? This is the least square optimal line, or the least square optimal vector that minimizes all these distances. That's just the vector that goes along the highest variation. That's what the PCA does. Okay, and how do we get those? This is simply the eigenvectors of the covariance matrix, right? And these vectors here, they're normalized, so it forms a nice basis. Okay, right. Covariance basis, how everybody knows it, right? So we have the first thing what we do is we have this mean, what I just said, right? We mean normalize everything. So everything is going to be used here as this mean normalized part. And then we compute the covariance matrix, which is straightforward. It's just x times xt. These are vectors. And this one then gives you a matrix, right? So it's the outer product between those two vectors. Then you divide it by how many you got here. 1 over n minus 1. And then you compute the eigenvectors and eigenvalues of the covariance matrix. Just as an example, right, I don't want to talk too much about, I hope that you know the PCA, by the way, and I know that if I'm repeating it, this might be something that you have heard many times, but it's just such an important fundamental concept that I decided to still put it in here, right? So typically use PCA for things like, I don't know, computer bounding box, right? Or do these kind of dimensionality reductions, what we're doing. So for the bounding boxes, by the way, right, same idea, right? What you do is you find the vector with the highest variance. This is the eigenvector here of the first basis, second basis, and so on, right? And so on. And this gives you an object-oriented bounding box. And in our case, the PCA basis is doing exactly the right thing, what we're looking for figuring out which of these axes here have the highest variation respectively in shape or in albedo space. And if you remember, all of these sliders I've shown you at the beginning, these were simply coefficients of the eigenvectors of the spaces, right? And the PCA is independently, in this case, computed for the shapes and for the albedo. And once we have it, again, these are our sliders, new phases can now be simply computed using a linear combination of these basis vectors, right? So if you're looking, let's do the albedo first, that's just a little bit easier. And the albedo is just taking the beta as input. These are our coefficients for the albedo PCA. And the albedo PCA is nothing else but here, the E-alb. These are our albedo PCA basis vectors. It's just the eigenvectors in the albedo space. And then you can multiply it with the respective coefficients, and then you can produce new albedos at the end of the day, right? For the geometry, it's a little bit more complicated because now we have both shape and expression coefficients, right? And we have just principal components here for the identity and for the expression respectively, and they are being parameterized independently. Again, be careful. There's different variations of this. This is the naive thing. You can encode the expressions either as delta vectors, you can implement them from scratch, and so on. So there's a couple of different variations how the expressions are being added, but this is just the simplest way I wanted to show you, right? And again, so what we have is we have the shape average here. This is this one. We have the albedo average here. And from this average phase and the average albedo, we're just computing the respective deltas from the identity deviation and from the expression deviation and from the albedo deviation currently, right? Okay, and this is what we care about. This is what the PCA gave us, and I think this is pretty straightforward actually. Well, it's not that straightforward, but the hard part actually is like this non-rigid registration has to be pretty good. If this non-rigid registration doesn't work, then the PCA doesn't work either afterwards. The one thing, what's kind of interesting, right? The number of principal components here like goes down very quickly actually, right? And at the beginning, the first few ones, they matter the most, and then it gets smaller and smaller. It's kind of yeah, it's kind of funny, right? It's like the way the standard deviation here is computed, because like the first principal components, they represent the most variance, right? So they make up for the most changes in the phase parametric model. Okay, and this property is kind of interesting here because we can basically reduce it for compute time. And remember when I showed you these videos at the beginning of the lecture, this is why you can, for instance, just use the 8 first principal components here to span the space of the phase model, which is kind of reasonable, I think. Okay, right. So this is how we compute it, and you can decide how many of these you want, basically, how much detail you can represent. I should say one thing: if you want to have really high quality phase parametric models, you need more principal components. But if you have more principal components, then the regularization effect of the phase model is not that great anymore, because the fewer you have, later on the fitting will be just a little bit easier. And I think that's kind of funny. Okay, so the expressions we haven't talked too much about, right? But this is also from the phase warehouse. They have the same idea, right? So now they're doing kinect fusion scans for each of the different expressions. They're recording those ones, and that makes sense. And now what you can do is, for the expressions, you can do the very same thing what I've just said. You can do a Pca representation. In this case, actually, you have kind of this loss of semantic meaning, but you can use it to compress data. And the one thing what I said is what people typically do is a little bit different. They use these delta blend shapes, meaning they use vertex displacements of a specific expression relative to the neutral phase, right? It's kind of like using a linear combination to interpolate between the expressions for the Pca. I mentioned this before, right? It's very straightforward. And this idea, you can kind of keep the semantic meaning, but now it's a Pca based on the expressions. That's the delta relative to the neutral pose, right? And then you can also do things like, oh, we can transfer expressions to another blend shape model, right? So in other words, basically, if you want to do expression transfer, and you have two people, and you have 2 blend shape models here, and you want to transfer from one to the other, then you can use these delta blend shapes in order to just copy the blend shape vector from one to the other, and you kind of get the expression from one person transferred to another expression. And I think that we will see later when we do facial reenactment. This is a very important property we're going to talk about a little bit more. Okay. Yeah, I guess I talked about how to compute those. We talked about the Pca basis. We talked about the Pca basis for identities. Talked about it for expressions. And yeah, we haven't talked about a runtime fitting to the input data. Runtime fitting, that would mean basically we have to optimize for these parameters of our parametric model. But I wanted to quickly clarify what I mean by that. With all of these parameters of this model, what we can do basically is we can now go ahead and say, well, we have this 3D phase. And this 3D phase is essentially defined by these parameters P, right? These parameters P here, like the pose, the shape, the albedo, illumination, and expression. This is our parametric phase model. And this parametric phase model tells us how to create something we can feed into a rendering pipeline and create a 2D image out of it, right? Pca's input determines the image. There's a bunch of stuff in between that have to happen, right? So first of all, it has to happen, oh, we have to apply the pose. Okay, so we have a mesh, right? We have the pose. Well, sorry, it's the other way around. So first of all, we have our blend shape basis, we have our morpho model basis, we have our alphas, betas, and so on. And we can use those ones in order to skin and produce a mesh out of our basis. We can then use our pose in order to transform it accordingly. And then we can go and also apply the illumination in order to light it accordingly. So, and then we have a mesh, we have lighting, we have albedo, and so on. And we can feed this into a rendering pipeline, and we're going to get an image out of it, right? So, in other words, what we're having is we're having these parameters P. They essentially define what our image is going to look like. This is why I'm calling this one here an image formation model, right? So P determines how the image will look like. Okay, and now the important thing is, why on earth did we build this model, right? Of course, for modeling purposes, people use it. But the really big thing that I care about is how to do reconstruction with it. right? It's this whole dimensionality reduction. Now, if we invert this process, and the idea is we can actually invert this process because these parameters P here that we have here, right? These parameters P, they are a low dimensional approximation of the phase. So we might be able to figure out a way how to go from a single input image here and figure out a way how to find optimal parameters P here that produce this image. And we want to do this ideally from a single image. Might want to do it first from a few images, not just from one, but ideally we would love to do this from a single image, right? And this is what we're going to talk in the next lecture. So in the next lecture, we're going to talk about how, given an image or a video sequence or an RGBD sequence, how do we reconstruct or how do we find the parameters P that define the phase reconstruction that we use this parametric model for. And this is what we're going to continue next lecture, and I think that's going to be super exciting. Okay, so this lecture was a little bit shorter, but I wanted to keep it shorter because if I had added this one in, then it would have been way too long. So I'm going to continue with this in the next lecture, and I think that's going to be super exciting. As usual, I have a little bit of reading homework. Specifically, I would love to have you look at the morphable model paper from Plants and Feather. This is just such a fundamental paper that everybody has to read it at some point. And I know that I've mentioned it a couple of times now. I again want you to look at Pca. I want you to understand the correlations to SVD and covariance matrices. Part of it I've had in the slides here, but I made it relatively short and concise because it depends a little bit. Some people already knew it, and a lot of people might have to read it up again. And I think this is just such a fundamental concept that please make sure that you really, really understand how a Pca works. It's just so fundamental. It's important for this course and many other courses beyond. All right, next week, we're going to talk about the reconstruction and the tracking using our parametric models we've been doing. See you then, and thanks a lot for joining and tuning in.